So, welcome back to the Advanced SQL course and greetings from the Resistance base. Time for another construct to add to the mix, and in this part of the course we will talk about aggregates. Aggregates are the method in SQL to summarize a set, a table of values, and derive a single aggregate, a summarization of these values. Think about summation, or think about computing the maximum of a table or a set of values. This is what aggregates can give us. The select from where clause, as we have talked about it until now, cannot do that. Any row that passes the where predicate filters will contribute one row to the result. And it's different in aggregates. Many rows, and we can control how many rows exactly are being considered. Many rows will be condensed into a single aggregate value. Okay, so that feature is called aggregates in SQL, or aggregate functions, but we will just term them aggregates here for briefness. All right. In the most simplest form for these aggregates, the collection of values that is being condensed into a single value is the entire table, or more precisely, all the rows that are extracted by the from clause and then admitted by the where predicate. There's no where predicate in this particular schematic query, but you get what I mean. So the aggregation, of course, happens after the filter predicate has done its job. So in the simplest case, the entire set of rows that is derived by from and where is being fed into the aggregate functions. And as you can see here, in a single select clause, I can compute many aggregate functions at once. Be aware, though, that if I decide to compute one aggregate here, then all of the expressions, all of the columns, all of the fields C1 to Cn have to refer to aggregate functions, and that makes sense. If only a few of these fields would compute aggregates and other fields would just return normal expressions, then we would have a clash. The aggregates would insist in returning a single value, or the other column fields would insist on returning one value per input row. So which of these many values should we pick? We are allowed to return only a single row, so either you run an aggregate query or you don't. There is some comments to be made on this when we talk about group bys, but for now that's the rule of the game. Aggregates or not, but no mixture. So what exactly does such an aggregate do? Let's look at the particular simple query here, where we only compute a single aggregate, and that easily extends to a select clause in which a number of aggregates is listed. So we are drawing tuples or rows and term them lowercase t when we have drawn them from this playground or any table T actually. And then we feed them into this aggregate function. The aggregate function as a parameter has some expression e. And normally, of course, e would refer to row variable t, so that it can extract certain fields from the row t and then feed these extracted fields into the aggregate function. And the result of the whole thing will be called C then. What happens internally is that different components of the aggregate functions are being invoked. To define the behavior of an aggregate function, it would actually suffice to look at this triple of defining characteristics of an aggregate. The first would be the value of the aggregate if it's evaluated over the empty value collection. So feed no value into an aggregate function, what will the result of that aggregate be? And this symbol, this empty set symbol with a superscript agg, that would tell us the result of the aggregate over the empty collection. Okay. If the collection is non-empty, then there is at least one value to aggregate. Before we start aggregation, we initialize the aggregation result with this aggregate specific 0 value. It's the aggregate value initializer. Then later, when more values come in, when the first, second, third value of the collection that we're aggregating over comes in, we will use the merge function, this plus in a circle, the merge function of the aggregate to take the current aggregate value, maybe it's the 0, the initializer, take the current aggregate value, add the new value that we've just seen to that aggregate value, and save that aggregate value as an intermediate result. If more values arrive, we will use merge repeatedly to further aggregate, to further merge more values into the aggregate state to arrive at the final result then. So if you prefer to read pseudocode, then that would be the pseudocode expression of what we have just described. We start out with an aggregate value A that is initialized by the empty aggregate value. So we are not sure whether we will see any row at all. So we initialize the aggregate value to the value for the empty value collection. Then we start iterating over the rows T of capital T. For each of these T's, we evaluate the aggregate expression E, this expression. And as I told you, E will probably refer to the row variable T, and that's what I'm depicting with the E and the parenthesis T here. E is a function of T in a sense. This will compute a value that we need to add to the aggregate, x. But first we check that x is not the null value. If x is the null value, it's going to be ignored. Almost all aggregates that we will describe here behave like that. If x is the null value, it will not be added to the current aggregate state, but simply be dropped and ignored. If x is not the null value, then we check whether this is the first x that we have seen. The first x that we've seen. If this is the case, then we will initialize our aggregate to the 0 value. Otherwise, we simply add x to the current value of the aggregate using the merge function. This gives us the new result for the aggregate, and we will do that. We will iterate until we exhaust the row source T, and the current value of A at this particular point is the result of the aggregate computation. So I think that should be rather straightforward. If we disregard this special treatment of nulls here, which leads actually to ignoring of nulls for most of the aggregate function that we have in SQL. This table would provide an overview of some of the aggregate functions. You see the dots at the bottom of the table here. These are there for good reasons, because the family of aggregate functions defined in modern SQL dialects is really extensive. But this table already lists the more common aggregate functions. So the count aggregate functions actually counts the number of values that we feed into it. So we start out with a 0 value of 0 of null. Sorry, let's say 0 here. And then for each value x that we see, we disregard x. We just simply maintain the aggregate and increase it by 1. So that will count the number of elements in the collection that we are iterating over. If that collection is empty, we return 0. So the integer 0. The cardinality of the empty collection is 0. That makes sense. Other aggregates behave a bit differently. So, for example, the sum aggregate will start out with the value 0, but then of course add x itself to the running sum that is currently being maintained, and we will provide and compute the sum of all the values in the collection as a final result. Should the collection be empty, then the sum aggregate will return null, not 0, but null in this particular case. That's the design decision by the fathers and mothers of SQL, as sum aggregate over an empty collection yields null, not 0. Maybe 0 is something that you would have expected. I would have expected this at this particular point, but the definition says sum over an empty collection yields null. And it's like that for all the other aggregates that you see here. The average value of a collection, the maximum minimum value of a collection, all of these return null if the collection is empty. You can see how the simple initializers and the simple aggregate merge computations look like in this particular case. For example, for the maximum computation, we start out with the minimum value of the domain that we're aggregating over. So the very first value that we aggregate will actually replace that minimum, this minimum value, and will lead to the proper computation of the maximum there. Okay. There's also Boolean aggregations, namely universal and existential quantification, which start out with, of course, Boolean zeros, and then use conjunction and disjunction to maintain the universal or the existential aggregate in this particular case. And they will, of course, yield a Boolean value in the end. We will look at an example in due course. Okay. There's one special form of the count aggregate. One special form of the count aggregate that that is not concerned with the actual value that are being counted. So, for example, null values will not be disregarded by this particular form count star of count, while the aggregates, as I've shown you on the previous slide, normally disregard null values. So even this count here would disregard null values or not count them. A count star really counts rows, completely disregarding any row contents, whether a row contains nulls in particular fields. Count star does not care. Count star counts rows, and we will also see the distinction in example later. Okay, so what would these aggregates yield if we apply them to the playground table, for example? And the answer is found in this particular slide. So we are iterating over the rows T of our playground table. We could apply a predicate P at this particular case. So at first, let's assume that P lets just any binding pass assume P equals true, like in this particular case. Okay, and then we compute a sequence of 6 aggregates here. As I told you, one select clause can compute many aggregates. The counting of all rows using count star, the counting of D values that are non-null, this might be less than count star, of course. The sum of all D values that are non-null, their maximum, and a Boolean universal quantification over the Booleans that are found in the C column, or a Boolean existential quantification over a predicate that checks whether TD equals 30. So if TD not equals 30, this will yield false. If any TD equals 30, this will yield true. The entire existential quantification will yield true if we can find any D value whatsoever that equals 30. Okay, so if this is the case, then this is the correct result for our playground table. It contains 5 rows, but only 4 non-null D values. The sum of these non-null D values is 100. 10 plus 20 plus 30 plus 40, that makes 100. The maximum in the string value column is y. Y is larger than x. There are, of course, some false values in the C column, some false Boolean values, so universal quantification over them will yield false. And in some row there must be D must equal 30 because the existential quantification over this column yields true. So let's check whether we can see that in the live PostgreSQL instance. This is the query that we were just looking at, and I've set the predicate P to true here, just as in the first part of this last slide. So let's evaluate that, and that's what we see here. Okay, so just the result that we have seen on the slide. So let's now check what happens if no row passes this predicate, and that means that we are aggregating over the empty collections. Now the aggregates are evaluated over the empty collections, and we will see their behavior over an empty set of values. Okay, so the empty set of values contains no rows. The empty set of values contains no non-null D values. And as I told you, as I shown you on the table in the slide before, the other aggregates yield null as a result if they are evaluated over the empty set. So the maximum is null, the outcome of these Boolean quantifications is null, also the sum over the empty set is null. Some of you might expect it to 0 here, as I told you, but the definition of SQL says no, the answer is null. All right. Okay, so let's check whether any of these d values is actually 42, which would be the right thing to be as a d value. Oh, I'm sorry. Of course, feed some rows into the aggregates. No, there is no such d value. The existential predicate yields. Okay, we should have. Okay. Maybe somebody is watching this video, is better fix the column name here. Okay, so no value in the D column actually has the value 42. Okay, that's sad, but it's a fact. For most of the aggregates that you have just seen, if you look at the merge function, then you will see that the merge function is actually commutative. The merge function in the case of sum or count has been just addition in a sense, and addition is commutative. That means that it doesn't make any difference in which order we feed the rows into the aggregate. The outcome of the aggregate value will always be the same. The same is the case for the quantification, the Boolean aggregations. It's the case for the average. It's the case for the maximum minimum computations. Almost all of these aggregate merge functions are commutative. We can feed rows into these aggregate functions in any order whatsoever, and we will receive the same result. There are other aggregates in SQL, the order-sensitive aggregates, that are really picky about the order in which the values flow into the aggregate function. And this is the case if their merge function is not commutative. There is one example of such a merge, of such an aggregate function, which is called string ag. String underscore ag concatenates a series of string values into one large string value, as you can easily imagine. And effectively, the merge function of this aggregate is string concatenation. String concatenation is used to start out from the empty string and then gradually expand that string into a longer string that is being returned as the result of the aggregate. The string aggregate function gives us the possibility to separate the individual strings that make up the aggregated value by some separator string. And you see in my example here, as a separator, I'm using the comma. Okay, I'm aggregating over the A values in my playground table. The A values are of type int, but I can cast them to something of type string or text here. What I get here from this expression is one of the string values I will concatenate together, separated by comma. And since string concatenation is not commutative, the order in which the aggregation happens indeed makes a difference. And these order-sensitive aggregates give us the possibility to add such an order by modifier. An order by modifier inside the parentheses of the aggregate expression. Okay, and well, the semantics should be obvious. Aggregation will happen in the order specified by this ordering criterion. So in ascending D order for this particular example. And that would be the result. Aggregating over all rows of the T table, nothing is being filtered away here. In the order of the D column, I will aggregate all the A values into a large string. So what you see here is one large string that has been aggregated. The different contributions of the rows are separated by commata, just like we have requested. And this is the value of this ordered string aggregate. I brought this ordered string aggregate with me here, and we can evaluate that for good measure. Let's see. Let's check actually of this, whether this is correctly reflecting the state of table T. Okay, so we were aggregating the values in the A column 1, 2, 3, 4, 5. Okay, and we found that in the aggregate. But in this particular order, 1, 5, 3, 2, 5, Okay, so the 1 is in the beginning, that's fine, because that's the smallest d value. Then the 4 with associated with d value 20 can contribute next, and so on. So 1, 4, 3, 2, 5, that would be the order in which the aggregation happens. If we change the ordering criterion of the ordered aggregate here and switch to a descending order, then we should see a different order in which the string contributions of the individual rows have been assembled to form a larger string. Okay, let me undo that. That's perfect. Okay, so we had this order by modifier that could be used to influence the behavior of ordered aggregates. There are other modifiers in modern SQL dialects that allow us to exercise control over what is actually being aggregated. These modifiers, they apply to any aggregate, ordered aggregate or not. You can use filtering and the unique modifier to aggregates to control which values actually may contribute to the overall aggregate value. This filter where clause attached to an aggregate does exactly what you think it does. It establishes an additional predicate in addition to the condition that the values e that we are computing have to be not equal to zero, not equal to null. I'm sorry, not equal to null. Non-null values are being aggregated if they also satisfy the predicate p. Okay, so if you recall the pseudocode of the earlier slide that we've shown you, we were checking for null there, for x being not equal to null, and we guarded the application of the merge function of the aggregate by this particular predicate. Now we use this conjunction of two conditions. X also has to satisfy predicate p, otherwise it may not contribute to the overall aggregate value. Okay, and another control that we can exercise over what is being aggregated is this distinct modifier that can be used inside the aggregate expression. And again, this does what you think it does. Only distinct values will be aggregated. Okay, so you normally find this in the conjunction with the count aggregate. Count distinct of an expression would only count the distinct values that expression e is returning. Okay, we will see an example in a few seconds. We can use all here, replace this distinct modifier by all, which would be the default, by the way. So we don't need to specify all, but we could specify all to document that we expect expression e to return duplicates, and that all of these duplicates should contribute to the overall value of the aggregate. All right, so let's see how this is going to work in practice. Okay, so here's an example query again over the playground table, the 5 rows that the playground table can contribute. And this is the form of aggregate that we have seen until now. Aggregate all the non-null d values that yields a value of 100 as we've seen before, unless we specify a particular additional filter and also insist on the C value of the aggregated row to be true, where TC will look at this Boolean column C. Only the true values in the C column will, only rows with a true value in the C column will contribute to the overall aggregate. So let's see how this influences the aggregate value. Okay, so if we don't care about the C value, we get the overall aggregate of 100 as before. If we are picky, then the aggregate only yields 50. So let's scroll back to the T table. C is true in this D10 column, and it's true in this D40 column. Together, this is 50. Yes, makes sense. Okay, so a filtered predicate in this case. Some consider this filter where attachment to aggregates syntactic sugar that is actually not quite necessary. You could express such filtering of aggregates in using regular SQL constructs that are available anyway, and this is true. So here's an expression of the same query using the case when construct. This is a conditional expression that has been part of SQL for a long time. And we could use that to express the filtering that the filter where clause was providing to us. Only if TC is actually true, we will evaluate this then part of the conditional expression. So if TC is true, then TD will be the result of the conditional, and the TD values will be summed up. If TC is false, we will contribute 0 here to the summation. So the summation will disregard the D value, and it will not affect the overall aggregate. We could as well place null here, and you may think about why this is the case. And this is our regular sum aggregate, and we get the same result in this particular case. Okay, so this is the filtered aggregation. Filtered aggregation can be used to good measure to perform something that is sometimes called pivoting. So pivoting actually refers to the act of turning your head 90 degrees and turning what has been represented in rows as being represented in columns. These filtered aggregates give you one way of expressing such conversion of things that have been represented in individual rows into a representation that uses individual columns. So for example, we had different rows that were carrying X or Y values, string values in the B column. So different rows were carrying these different B values. Using these filtered aggregates, we will select these particular subsets of rows and let them contribute to the sum aggregate in this particular column. So particular rows contribute to a particular aggregate that we are building up in this column here. This is the D value sum in the region X, or for all rows that carry X in column B, this is the region Y sum of D values. And any row that has a B value not in X or Y would be contributing to this third column, the elsewhere column that we are building up. We know from looking at our playground table, there is no such row that would satisfy this predicate. So let's see what happens. Okay, so the value, the sum of the D values in the X region, or for the X rows, is 40. For the Y rows, it's 60. 60 plus 40 already makes up the 100. So there is nothing that any other row could contribute. We are aggregating over the sum aggregate over the empty set here, and that yields null. Okay. A more general version of evaluating aggregates for different sets of rows in a table, for the Y rows and for the X rows, for example, is being presented when we talk about the group by construct in SQL in the next video that we are producing just after this. Okay, and as a final bit, the demonstration of the count and the count distinct, you see that here I'm counting the non-null C values. The non-null C values, I think there are indeed 5 non-null C values, Boolean values in our playground table. But since C is a Boolean column and the value set of a Boolean column can only contain 2 distinct Boolean values, we will see a value of 2 here for the count distinct aggregate when we evaluate this example. Okay, so there are 2 distinct non-null Boolean values. That's no surprise, but overall there are 5 non-null Boolean values in our playground table. Okay, so much for that. That's aggregates. Aggregates over entire collections of rows, unless we use some filtering to disregard some rows. And we will generalize this behavior of aggregates when we talk about grouping, as I just told you. But that's a topic for another video. And See you then.